Hello dear students, welcome back to my YouTube channel. So yesterday we had to reschedule our session, right, due to some sort of network issue. So we will be shifting our classes in the morning so that to just avoid these network issues and all these things. Okay. So this is a good time, 10 o'clock in the morning. Okay. Am I audible? Okay. So I guess in the previous lectures we had discussed some derivations, no? I guess we had complete all the derivations, the due to point charge, due to linear charge density wire, and different cases of that, right? Then we had the discussion on circular ring. Then we had the discussion on circular arc. Okay. So if we talk about the point charge, it is what electric field kq by r square. If we talk about the line charge density, it has two components. One is the perpendicular and one is the parallel. Perpendicular is k lambda by r sine theta 1 plus sine theta 2. If we have the parallel one, that is k lambda by r cos theta 2 minus cos theta 1. Okay, then we have the cases how to find for infinite line or semi-infinite line. Then we had one case for circular arc, right? 2k lambda by r sine theta by 2 or sine alpha by 2. Then we had a ring, the axial position of the ring. It's kqx divided by r square plus x square 3 by 2. Okay. I guess up to this particular point we had the discussion. So let's continue from that particular portion. One second. Okay. Okay. You can see. So we had the discussion of the plan, na? So we need to just change plan that 10:30 p.m. to 12 o'clock a.m. right? And we need to change this. But yeah, we will just complete the whole syllabus up to the September of 2025 of your 12th. Hello, beta. So yeah, up to this particular point, we had a discussion of water suspended particles. Then this one, then electric. Oh yeah, we had also discussed the electric force. Okay. Okay. So now let us start. Let us start from one topic, a very important one also. So we can start with the electric field lines. With what? Which topic we had here? It is electric field lines. Electric field lines. Okay. Electric field lines. So basically, now we know that around a charged particle, it has its own field. In that field, if we have any other charged particle, that charged particle will going to feel a force of attraction or force of repulsion. What are these electric field lines? What are these electric field lines? So these electric field lines are imaginary lines. What are these lines? First point, these are imaginary lines. Imaginary lines. Okay. And what these lines represent? Now, look, beta, if we have a positive charge here, let's suppose we have a charge positive here. Done? So we know that around this charge particle, it has its own field. Let us bring a charge particle Q naught. We have a Q naught here, plus Q naught. Let us bring it here. Let us bring it here, right? Here. I guess due to the mutual repulsion, this charged particle will feel a force of repulsion. So the charged particle will go, I guess, in this way. Okay. If I just release the charged particle at the particular point, now, if I release this charged particle, at this particular point, point number A, it will go along B. Why? Because due to the force of repulsion, my charged particle will go from A to B. So this dotted line shows a road. These are roads, right? These are roads. The dotted line represents a road. If a charged particle is free to move, so it will move along this line only. it will move along this line only. These lines are basically imaginary lines. So these lines are called electric field lines. These lines are called as electric field lines. Okay. So electric field lines are basically what roads for our charged particle to move on it. These are basically imaginary lines. Okay. Look here. So look, every time my charged particle is positive, so it will go along this line. Look, the line is like this now. The arrow shows the direction of line. If my charged particle is here, I guess it will go in this way. Yes, sir. Now, if here I have a negative charge, if I have here a negative charge, what will happen now? The negative charge, if my charged particle is here now, okay, the negative charge particle will attract it. So my charged particle will come in this way. Okay, so it will feel a force in this way. So this one is also a what? A road. For what? For this charged particle to come closer to the negative one. This one is also called what? Electric field lines. Hello, Sumara. Hello. These are also known as what? Electric field lines. That's why you have heard or you have read about that electric field lines originate from positive and they terminate at negative. Look, now it goes from positive. Look, it is from positive. From positive. Why? Because charged particle get repelled. And it is towards the negative. Why? Because charged particle will go towards the negative due to force of attraction. Very easy, no? So these are basically imaginary lines. These are basically imaginary lines. Number second point. They originate. These lines originate from positive and terminates where? At negative. So my electric field lines originates from positive and these electric field lines terminates at negative. Okay. And my electric field lines, I can write here, they will never close loop. They will be never closed loop. Never closed loop. They will form never closed loop, right? But this sentence is not always correct. Look, if we talk about this particular one, this one is not always correct. Do you know why? Look, I will give you an example for that. Look, if we talk about electric field, we have two types of electric fields. Two types. One electric field, we have it due to the charged particle at rest. Okay. If we have my charged particle at rest, one field. One more is due to the induction part, or I can just call induced magnetic field. We know that whenever there is a change in the magnetic field, it will create a electric field. But that electric field will be in the closed loop. So yes, if my charged particle is at rest, so I can write here never form closed loop. Never closed loop. Done? But if we have induced electric field, induced electric field, this one is always closed loop. Okay, this one is the important point here. Okay. हाँ बेटा, बेसिकली शाम को आई गेस कुछ नेटवर्क इश्यूज आ रहे हैं ना, तो शाम को कुछ अच्छा नहीं रहता। जब तक वो ठीक नहीं हो जाएगा तो we had to shift to the lectures in the morning. So look, so we were talking about the electric field lines. So if the charged particle is at rest, so the electric field associated with my charged particle at rest, it would be always, it will not be in closed loop. But if my charged particle is in motion, That means if we have the magnetic field variable, so that will create an induced electric field. In that induced electric field, my electric field lines will be in the closed loop always. Okay, so this one is for your entrance examination point. Now next point number 4, tangent. If we draw a tangent on electric field lines gives direction of field. Direction of field. Look, how? Look, if same way we have here, let me show it 1 second. Okay, if here we have something like this. Now, if this is my line, okay, this line represents my electric field lines. Okay, so now at this particular point, I want to get my direction of electric field. So how I will get it? I need to put a tangent here. Look, I will put a tangent here. So this particular tangent will give me direction of my electric field. Okay, just like in circular motion, na? If my in circular motion I need to find the velocity vector, na? So we were in a circular motion, we need to draw a tangent at that particular moment. So we got a direction for that particular velocity. But I am teaching in an academy, right? I am in one of the academies. Don't worry about it. I am taking some paid courses there. Okay, ऐसा नहीं है. If you want to join my courses, na, you're most welcome. Clear? So tangent will give you the direction of my electric field. Now, fifth point. Fifth point is interesting and most confusing one. How? Look, electric field lines never intersect. Never intersect each other. Never intersect each other. Do you know the reason why? Okay, because you have heard about, na, sir, if electric field lines do so, then there will be a two direction, na? So that is not possible. Why is it not possible? Look, what is the meaning of it? Now look, beta. Suppose we have here, look here, this is my one electric field line. I guess this electric field line shows that if I have a positive charge here, if direction is like this now, if I have a charge particle here, the charge particle will go along this line only. This charge particle will go along this line only. Okay, if it is at rest initially, it will go along this line only. Clear? Now let us think about that. No, for a particular time being, let's two electric field lines meet each other. So let's make a one more line like this. Look, okay, that means a charged particle will go in this way. Look, okay. Now look, if we want to get the direction of this one, so here, this is my electric field. Clear? And due to this one, this is my electric field. Look, either my charged particle will go this way or this way. But if we have two vectors, between them angle is theta. Between them angle is theta. So my charged particle will go in this way. Okay, in this way. My charged particle will go in this way. But this is not possible, no? Either my charged particle can go in this way or in this way. It won't get in this way, no? That's why it is not possible that two electric field lines intersect each other. It is not possible. It's very easy. Next point. Point number 6. Point number 6. Point number 6 is number of electric field lines or electric lines of forces directly proportional magnitude of charge. Okay, number of electric field lines or number of electric lines of forces directly proportional to the charge magnitude. It simply indicates that, look, beta, if we have a charges here, let's suppose my Q1 is here and my Q2 is here. Okay, I will make now, it is electric field lines. Look, 1, that means it is positive. Look, 2, 3, 4. Here, 1, 2, 3, 4, 5, 6, 7. Okay, look here. In the first charge particle Q1, how many lines we have? So we have 4 lines. These are outgoing lines. That simply indicates the charge is positive. Here we have towards it, it should be negative. No? So look, in the first case, we have 4 lines. In the second case, how many we have? We have 1, 2, 3, 4, 5, 6, 7. We have 8 lines. I guess in second case, my lines are more. So the magnitude of second is more to the first, according to this one. If we have more electric field lines, so which indicates that the magnitude of that particular charge would be more. Here Q2 is more than Q1. So therefore, I can write here mod of Q2 is more than mod of Q1. Okay. Simply. I guess point number 6, now point number 7. We have point number 7. Point number 7 is electric field intensity is inversely proportional. Separation between lines is inversely proportional. Separation between lines. Look for this one. What is the meaning of this one? Look now. If we have field lines like this, look. Now we have 2 points. Point number A here, point number B, and point number C. I can write here 1, 2, 3. Look here. I guess if we talk about point number 1, these electric field lines are closer. If we talk about point number 2, these are very distant. And if we point number 3, it is very far away. So if electric field lines at 1 is E1, sorry, electric field, and electric field at 2 is E2, electric field 3 is E3. So by this particular formula, I can write, sir, E1 is more than E2 and E2 is more than E3. The crowdedness of these lines indicates the stronger the electric field would be. Easy, no? If we have the electric field lines closer to each other, so that directly will give us the proof that yes, at that particular position, my electric field will be the stronger. It will be the stronger. Done? I guess if you have done some PYQs, na, you had got one numerical based on this one. Na? I guess a numerical was like this. Look, numerical was like this. It's a PYQ. Okay. Point number 1, point 2, point 3. So this is my question, and we have to choose one option. Look, we have to choose one option. Look, first option, electric field 1 more than 2 more than 3. Second option, electric field 2 more than 1 more than 3. Third option, electric field 1 equals to electric field 3 more than electric field 2. Fourth option, electric field 2 more than electric field 1 equals to electric field 3. So can you choose a pick of one option from the four options? Just choose one, no? You need to choose one based on the property that we defined it above. The electric field line intensity is inversely proportional to the separation. Separation more, intensity is less. Separation is less, intensity is more. Based on that, we had this NEET PYQ. This is a NEET PYQ basically. This one is that NEET PYQ. Which one is correct? Third option. Yes, third is more. Why? Because option number this point number 1 and point number 3 at the both points the separation between lines is same and close as compared to the second one. Yes, so we can write option number third is correct. Easy enough. If our basics are very clear, that there is no such issue that we are having apart. They're very easy. Okay. Now let's talk about the parallel electric field lines. Parallel electric field lines. So if you have seen a parameter known as parallel, or what is uniform electric field? If you have seen uniform electric field. Look, electric field lines are basically a representation. Basically, electric field lines are the representation of electric field. If you want to show my electric field is uniform, if you need to get my electric field should be uniform, we know one thing. What, beta? We know one thing, that is my electric field, it is a vector quantity. We know now electric field is a vector quantity. Vector quantity means it carries magnitude, and it carries direction. If my electric field is uniform, that means its magnitude should be same and its direction should be same. And if we have a line which shows the electric field, uniform electric field, so those lines should follow these two parameters. That means those lines should give you the magnitude as well as direction same. Look bit, I will give you some examples. Let's suppose in my first case I have like this now. Look, does these lines show my uniform electric field? Yes or no? Does these lines show my electric field uniform? Yes or no? Sir, how to get this one done? Look, first of all, we have to see, does all these lines have same direction? Yes, sir, all these lines have same direction. But what about the magnitude? You can see now, between these two lines and between these two lines, separation is same. But what about this one? Separation is more. That means this particular diagram shows non-uniform electric field. It is not uniform, it is non-uniform. It is, I will click on, no, this line doesn't show a uniform electric field. It is very easy, no? Okay. Now let's take second example. If we have now something like this, now look. If we have something like this, one, now tell me, does these lines represent uniform electric field? Yes or no? Yes or no? Sir, two parameters on behalf of what we can give it is guarantee whether it is a uniform or not. Yes, that is direction same. No, sir, these are diverging, right? Direction is not same. Look, at this particular point, it is going in this way. Here it is going in this way. Here it is going in this way, right? No direction same. All directions are different. Magnitude is also different. And look, the gap between here and the gap between here, different. So I can write it there. No, this line doesn't show the uniform electric field. I guess I'm audible now. Yeah, my voice is also clear. Now let's talk about the third one. Talk about the third one. Look now. This one, this case, look. Let us talk about this case now. I need to make them with some preciseness so that you can, one second. Now tell me about this one. Yes or no? Does these lines represent uniform electric field? Yes or no? These lines. Does these lines show uniform electric field? Yes or no? Huh? I need answer for this one, no? Check whether the magnitude between the lines, that means the gap between the lines are same, direction is same. So you can do one thing. You can do one thing now, sir. Look, I guess the magnitude is same between two lines and it goes the same and direction is always same. Yes, so you can write it as yes, these lines show a uniform electric field. Yes, the answer will be yes. Big yes. Yes, it is correct now. That means you know how to represent a uniform electric field. What is the pictorial representation of uniform electric field? Basically, electric field lines are the pictorial representation of electric field. No? Okay, one more example. One more example. If we have something like this, look. If we have something like this, look. Okay. What about this one? What about this one? Yes or no? What about this one? Yes or no? Does these lines represent a uniform electric field? Yes or no? Yes or no? I know there is some sort of time difference, so you need to just give me the answer for this one. For this one, yes or no? Does these lines represent uniform electric field? Yes or no? No. The answer is big no. Do you know why? Answer is no. Look, to represent the uniform electric field, two conditions should be same. One is direction should be same. Second one is what? Magnitude. That means the distance between lines. So look, sir, What one thing is same, na? That is, distance is same. Look, distance is same. Okay, but what about the direction? Look, here I will take a tangent. Okay, here is tangent. Tangent. Here, look, tangent. 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 Here, tangent. Is the same? Value same. You can write, sir, value is same, no? Value is same. But what about direction? Here direction is different, different, and different. So my direction is different. My direction is different. My direction is different. That's why these lines represent a non-uniform. Hello, Santosh. I know you. Okay. Look, direction of the electric field line should be same at every wire, no? It should be same. It should be same. But you can see here, sir, this direction is different, this direction is different, this one is different. So they should be in the same line, then only you can call it as a uniform electric field. Then you can call it as a uniform electric field. I guess now up to this particular point, everything is very clear to you, no? So how many points we have done? It was how many? 7th, 8th. Okay, 8. This was the 8th point, no? 8th point. Let's talk about the 9th one now. Okay, talk about the ninth now. Santosh is from English batch, no? Look now. One important one. This one is important. This one is very important. And this property is that if we talk about conductors, in conductors, electric lines of field or electric field lines cannot enter. These lines cannot enter. While in non-conductors, or you can try dielectric as well, few electric field lines can enter. If we talk about the conductors, electric field lines cannot enter. But if we talk about non-conductors or dielectrics, right? So few electric field lines cross or enter our material. Look, why? If we have two plates, let's talk about the reason of it. Let's talk about the reason. So what is the reason behind the particular property? So let's suppose we have a plate, one plate and one more plate. On this plate, I have charge plus Q. On this plate, I have charge minus Q. I guess these lines, look, I guess these lines represent electric field lines. Okay, these are my, let's go uniform electric field lines. Let us suppose. Okay. First case, we have conductor. First, I will put a conductor. Second case, I will put a non-conductor. I will put a non-conductor. One property that everybody should know now. That is, in conductor, if we talk about induction, there will be 100% induction. Done? If we talk about non-conductors, there will be a less induction. Induction is less. Induction is less than 100%. Okay. If we talk about conductors, in conductors, there will be a induction. I guess we had discussed what is the induction, no? There will be a 100% induction. But if we talk about non-conductors, the induction is less. Clear? Basically, now the reason for it, we have the equation. Now, do the equation? Equation is Q dash is equals to minus Q 1 minus 1 by epsilon r. This is my equation. Okay, you will get confused now. Let it be this equation. You will get confused. Okay. So now let us put a conductor between it. Let us put a conductor. Okay, I have a conductor. I will place a conductor. Look, I will place a first of all conductor here. Look, this is my conductor. This is my conductor. Look. So basically, here we have positive charge. Here what we have? We have positive charge. Here we have negative charge. Okay, that's why electric field is from positive to negative now. So due to this, what happens now? Due to this, what will happen here? Look, what will happen? I will write here, sir, this positive here. So this side I will have minus, negative. I will have negative due to induction. This is negative, so I will have positive here due to induction. Now here positive negative, it creates its own electric field. It creates its own electric field. It creates its own electric field. I can write it as a induced electric field. What is it? Induced electric field. Induced electric field. Okay. And this one, look, this one, what we have? We have external electric field. We have external electric field. Look, charges are same. This is what? This one is external electric field. This one is what? External electric field. Look at that. Charges are same. Na? This positive and this negative charge is same. This positive, this negative charge is same. So that means external electric field magnitude is equal to induced electric field magnitude. Due to which what happens now? The internal electric field will become zero. My internal electric field will become zero. Only my electric field will be present between the gaps. Due to which my electric field will be only present between the gaps only. Okay. Due to which electric field will be present between the gaps only. Inside the metal or inside the material, the conductor, it is zero. It is what? Zero. Okay. So you can write electric field net inside of conductor is zero. That's why inside, look, you can read this paragraph, no? In conductor, electric field lines cannot enter. Why? Because zero it is, no? At the end it is zero. Now let's take the second example. If we have the non-conductor now, very easy, no? If we have the non-conductor now, okay? If we have the non-conductor one, look, this is what? Plus Q charge. That means here we have plus Q charge. Here what we have? We have a minus Q charge. So minus Q. Okay. We know that there will be an electric field, no? Like this. This is my electric field. As usual between positive and negative. My electric field. Okay. Now when I place a non-conductor like this on these two faces, this face and this face, what will happen? There will be an induced charge. There will be an induction or induced charge. Here we will get minus Q dash. Here I will get plus Q dash. But induction charge will be less than the original one. Original charge. So you can write due to induction charge, my electric field, my induced electric field will be less than the original or the external electric field. So you can write, sir, my net electric field inside non-conductor is not equal to 0. So here what will happen now? What will happen now? I will write, look, what will happen now? There will be some charge. Let us suppose this charge is like this. Okay. Here we may have some more charges. Look. Here we have some charge. Not more than some charge. Okay. So it will be look like this. Okay. Yeah. Between the non-conductors, some lines may be present, but not everyone. So, but in case of conductors, 0 line is present. In case of non-conductors, some lines will be present. Easy? Okay. Let's suppose we may have a hypothetical situation. Let us manipulate the whole scenario now. Let's suppose we have a hypothetical situation in which we are assuming now inside the conductor my electric field is not 0. Let us assume inside the conductor my electric field is not 0, and inside the conductor my free electrons are present. Assume, na? Let us assume. Okay? Let us assume. Interesting point now. Assume. What's the 2 points? Inside conductor, free electron present. And inside conductor, my electric field is not 0. These two conditions. We know that whenever there is electric field, and in that electric field, if we have any charged particle, just think about it. Whenever we have electric field, and in that electric field, if we have a charged particle, that charged particle will face a force. Look now, if here I have my electric field, suppose this is my electric field, suppose. And in the electric field, I have a charged particle here, plus Q. I guess this charged particle will face a force. And this force is equals to charge into electric field. Yes or no? Yes or no? Due to this particular force, my charged particle will come into motion now. It will come into motion now. This charged particle will come into motion now. If this charged particle will come into motion now, free charged particle moving, that means there will be an electricity. There will be a current electricity. Without applying the external battery, without using any sort of battery in my circuit, charged particles automatically flow, and we are getting electricity without consuming the battery and the cells. Is it possible? It is not possible. It is not possible. Done? We cannot produce current without applying the sources, battery or cell. But here, if we assume, yes, inside electric field, inside conductor electric field is present, inside conductor charges are present. So then we have to correct our statement now that we can produce electricity without external electric field. Sorry, without external my battery or my cell. So that's why, due to which we know that without external sources we cannot produce electricity. So these two sentences are wrong. So these two sentences are wrong. Okay. One more thing. One more thing. Property number, I guess 9, not 10. 10 is also important. Okay. My electric field, my electric field, my electric field or electric field lines or electric lines of fields. These are always normal to conducting surface. Always normal to conducting surface. Normal means perpendicular to conducting surface. But if we talk about non-conductors, why? In case of non-conductors. But in case of non-conductors, any angle is possible. Any angle is possible. Okay. So the reason behind it is if we have my conductor surface like this. This is my conductor surface. We know that at the surface we have charged particles. We know it. Okay. So these positive represent electric charges on the metal slab. Now, if we think about, yes, my electric field is not perpendicular. My electric field is in this way. This is my electric field. I guess this electric field is making some angle theta on the surface. So I can just break down the electric field into two components. One is E cos theta. One is E sin theta. One is E sin theta. Look. Now, due to this E cos theta, my charged particles, okay, they will feel a force due to which my charged particles which were at rest will be in motion now. These charged particles will be in motion now. If my charged particles in motion now, so I can get my what? Electricity. I will get my electric current, which is not possible. Okay. I cannot create electricity here. That's why every time it is said that electric field lines or electric field should be perpendicular. Okay. The reason behind it, my charged particles shouldn't feel any force of a dragging. Okay. Look. So if my field is in this way, surface, angle is 90 degree. Angle is 90 degree. So what is cos 90? Sir, cos 90 is 0. So that's why at this 90 degree angle, my these charged particles won't feel any forces. So they won't get dragged. No? They won't produce then the electric current, which is correct. So that's why electric field lines should be normal to conducting spheres. In conducting spheres, we have the free electrons. That's why they need to be moved. No? So that's why we don't have any component of electric field. We should do this thing. But if we talk about non-conductors, it is possible. Na? Any angle is possible because their charged particles is not free to move. Okay. It is easy now. Okay. Now let us do one numerical from your NEET and from IIT. Very good numerical. Okay. Good numerical. Look now. If we have two plates, okay, one plate, one more plate. So on this plate, I have positive charge. On this one, I have negative charge. I guess due to this positive and due to this negative charge, I will have my electric field lines or electric field like this. I guess these white lines show the electric field. I guess I am correct, no? Okay. Now, I have a metal ball. What I have here? I have a metal ball. This is metal ball. Okay. I have a ball of metal. I guess metal is a conducting sphere. I guess metal is a conducting sphere. Now I need to place the metal inside this. What will happen then? What will happen? Look now. Solution. What will happen? Look, beta ji. These are my two plates. These are my two plates. I guess I'm not good in drawing my plates. Okay. And inside the plate, I need to put my metal like this. Okay. Look now. My electric field is in this way. My electric field is in this way. Okay. Is this right or wrong? Is this correct representation? Yes or no? Is this correct representation? Yes or no? Hmm? Just tell me. Is this correct representation? Yes or no? I will wait for your response. No? By your response only, I will get to know that you understood the upper topic or not. Is this correct? Yes or no? Think about it. No? Huh? Okay, I guess you are not in the mood to give me the answer, right? Yes, the answer is no. Savara, you are correct. The answer is no. Why? Look, if we can see here now, if we can see here, look, if we can see here, look, and here, look. I guess these angles needs to be 90° only. I guess these angles needs to be 90° only. But here, these are not 90°. So it is incorrect. If I need to make them correct, this is what? Correct? No, this is not correct. So how to change it now? How to change it now? Look, beta. How to change it now? Look. So my lines will become now, look here, like let's suppose like this, it will become 90° here. It is not 90° now. Lines need to be 90°. Oh, what happens to it? 1 second. Okay. These lines need to be 90°. As these lines and they don't cross my conductor also. This is my correct representation of it. Look, inside no electric field line is possible. And you can see here, sir, here also, here, here, angle 90 degree. Which one better? First point is, inside the metal, there is zero electric field lines. Second one is, whenever my electric field touches any metal surface, it will make a 90 degree on its surface. First point, inside metal, zero electric lines of forces present. Here you can see it now. Second point, on the surface of metal, every time electric field line should make 90 degree. Okay, look here. We were having a metal like this, no? Look like this. So it was present like this inside this one. But look, it contradicts with my upper two properties, no? These lines are present inside the metal, which is not possible. And these lines, look here, these lines are making any angle. Look here, no? These lines are making any angle. Look, this is theta, but it is not 90. Look here, theta not 90. First of all, theta should be always 90 degree, and inside there should be a zero lines. So how to get it now? How to get it now? Look, I will just change every scenario of it now. Look it up. So look, 90 degree, and it will come at 90 degree. Look, 90 degree. It will come from the 90 degree. Look here, 90 degree, and it will come from this one at 90 degree. Easy? Okay, let us do a numerical from IIT. We have a couple of numericals. We have a couple of numericals from IIT. So you will just feel how this particular one is important. Very simple. If we have a metal body, if we have metal body like this, okay, we have three representations. One line is going in this way. First line. Second line is going in this way. Look. 90 degree. One second. Third one. This one is not correct. One second. Out of 1, 2, 3, which represents correct electric field line? Out of three lines, we have 1, 2, 3, which represents correct electric field line. Which one is represents best electric field line? 1, 2, 3, which one? Out of 1, 2, 3, we have to choose only one option which represents correct electric field line. Give me the answer. Perfect, Queen, you're perfect. Answer is right. Why? Because whenever you want to find answer, now you have to think about 2 pointers. Inside metal, zero line is present. That means you need to discard this one now. Okay. Now we have 2 and 3. Second point is, on the surface, every time my electric field should make 90 degree. Look, this is not 90 degree now. This is not 90 degree. Discard. 90 and inside 0. This is correct. Yes, beta. Both are correct. Only second option is correct. Okay, one more example. Let's talk about one more example. If we have something like this, look. If we have something like this, look. Okay. Yes. If we have, it is solid, no? It is solid. Solid means inside material is present. Inside, no? Material is present. And on the center, we have charge minus Q present. Okay, Supreetha. Okay, beta. Your name is not written, no? That's why I'm using Queen, right? Your name is as Queen here. Okay, Supreetha. Okay. Now, how to make it is diagram? First of all, we know by the concept of induction, if here is minus Q, so on this particular side, I will get plus Q. Okay. Okay. Most appropriate, I can do one thing. If it is minus, if it is plus Q, no, that will be easy. Then you will get confused. If it is plus Q, so by the induction on the inner side, I will get minus Q. And I will get plus Q here by induction. So how to make now electric field lines? How to make it now? Look. How to make it? Look. Material present. We need to think about only one point. 2 points. No field present inside the metal. 90 degree. I guess it will be looked like this now. It will be in this way. Look, these are, look, at every point making 90 degree. Every point these lines are making 90 degree. 90 degree. Look, inside also 90 degree. Okay. And inside this, no electric field lines present. This is correct representation of it. But this is only possible when my charge particle is at what? Center. At center. At center or at origin. Okay. But let us suppose we displace it. Let us suppose we displace it now. So how it becomes now? Look. Let us suppose we displace it now. Look now. Okay. Now I will displace it. Here it is not at center, it is at this particular point. My plus Q is here. And here we have material. What will happen now? Look, we know that by the case of induction, plus Q, so on this I will have minus Q, here I will have plus Q. Look, how my lines would be now? Look, it will go like this. It will be like this, look, 90 degree. It should have here 90 degree. Look here, 90 degree, 90 degree, 90 degree, 90 degree. Okay, so these lines will be like this, 90, 90, 90, 90. So because here charge not present, charge not present at center. Okay, this charge particle is not present at the center. That's why I have to make it like this. Clear? Easy, no? Easy or super easy? Easy or super easy? I guess it's very easy. Huh? Very easy. So I will give you 1-2 minutes. If you have any confusion up to this particular topic, you can just let me know. Then we will start some sort of motion of charged particles. My topic would be motion of charged particles here in a uniform electric field. So next topic would be motion of charged particles in uniform electric field. If we are placing a charged particle in electric field, what will be my final velocity? What will be my kinetic energy? How the graph will looks like? How much distance my charged particle will travel? Or what will be my Q by M ratio? Okay, these things we will discuss now. Look now. Next topic is right here motion of charged particle in uniform electric field. Motion of charged particle in uniform electric field. Case number first. Case number first. When my charged particle is released, when it is released from rest, when my charged particle is released from rest, that simply indicates if my initial velocity is zero. If my initial velocity is zero, how we can get it? Look now. First thing, I guess force is equals to charge into electric field. We know this equation very well. And from kinematics, force is equals to mass into acceleration is equals to charge into electric field. So by this particular equation, my acceleration of charged particle would be equals to QE by M. It will be equals to QE by M. Done? Very easy. Now, how to find distance now? How to find distance now? I guess we know the equation S is equals to UT plus 1/2 of AT square. We know this one. Look, initial velocity is 0. So I guess S is equals to 1 by 2. What is acceleration? Sir, acceleration is charge into electric field divided by mass. Then I have T square. Okay. So this is my what? Distance traveled by my charged particle if placed in a uniform electric field. Second point. Sir, how to find the velocity now? For velocity, I guess V is equals to U plus AT. U is 0. So I can write V is equals to A. A is equals to QE by M into T. You need to remember these equations, how to manipulate. How to manipulate. Done? Sir, what will be my kinetic energy? What will be my kinetic energy? What will be my kinetic energy? Sir, I guess kinetic energy is equals to 1 by 2 mv square. It is 1 by 2 mv square. I can write here how much? 1 by 2. Mass is m. V square. I can write it is Q square E square V. Na? Then I can write m square into T square. 1m cancel out. So my kinetic energy becomes Q square E square T square by 2 times n. You don't need to remember all of these things. Just remember how to manipulate and how to get the answer. Okay. Very easy now. But I guess to derive these things, we had considered one thing, that my charged particle is released from rest, which indicates that my initial velocity is 0. Let us talk about the second case. If we are throwing my particle, look, Placing or released is something different. Throwing is something different. Now, if we throw my particle with some velocity u in an electric field, okay, case number second. Case number second. If we have an electric field, let's suppose my electric field is in this way. It is according to my NCRT. Okay. If my, okay, it is getting some sort of not good, so I will make it like this. One second, one second. Okay, if my electric field is in this way, look. I'm making my electric field. Okay, now I have a charged particle here. Here, I have a charged particle. I am just throwing the charged particle plus q with some velocity u inside this electric field. Look, what does this electric field represent? Look, the arrow is upwards. That means my electric field is in this way. This is my electric field. Okay, and we know that electric field is from positive to negative. Positive to negative. We know these things. Positive, negative. Positive, negative. Positive, negative. Then what we assume, what we just consider from this one now, when we just put it here with some velocity, so my charged particle will deviate from this path. Obviously it will deviate now. Why? Because it will get its force, because there will be a force on it. Huh? One second, what happens to my network? One second. Hello. We can do one thing now. We will take 3 minutes break here. Okay, and we will continue from this one. 3 minutes break. 3 minutes break. So let's continue our session. So let's continue from this particular part. Okay. Let's confirm if I am audible and visible to you. Okay. Look now. So we have projected a particle of Q into an electric field in x direction. So I can write here, look here, I can write here my ux velocity in x direction is u and my velocity in y direction is 0 because my particle is along going x direction. So no component in y direction. So my y direction component is 0. Done. And we know that my force will be in the direction of electric field. So if my electric field is upwards, so my force is upwards. If my electric field is upwards, my field will be upwards. So, but no force is in x direction. So I can write acceleration in x direction is 0. No acceleration x direction because no force is in x direction. No force in x direction. Now, what is ay? I guess we just now derive it. It would be qe by m. It is in y direction. Why? Because force is in y direction. Force is in y direction only. Okay. Look, for charged particle deviates this theta. If let us suppose this length is y, suppose, and this length is x. This length is y and this length is x. How to now do the calculation for the same? Okay, look better. Let us put some kinematics here. Look, we know one formula, that is, sir, S is equals to ut plus half of at square. So we have two displacement. We have displacement in x also. We have displacement in y also. So for x axis, I will write one equation. For y axis, I will write one more equation. For x axis, I will write Sx is equals to uxt plus 1 half of axt square. Okay, just like my 2D. I will write here Sy is equals to uyt plus half of ayt square. Look, the displacement is x direction is x only. Uy, the velocity in u x direction is u only. And time is t. 1 by 2. Acceleration is x is 0 into t square. I guess my equation came out to be x is equals to u into t. Then here, displacement is y only. Velocity in y is 0. Then here, what I have 1 by 2. Acceleration is y is equals to qe by m. Then it is t square. So y is equals to 1 by 2 qe by m t square. qe by m t square. Then So from this particular figure, I guess my t is equal to x by u. Now place this t value here. I guess y came out to be, it is 1 by 2 qe by m. Instead of t, I will write x square by u square. I can write like this now. So look, the equation or the values between y and x. So y is directly proportional to the x square. So the graph would be parabola. So the graph for the motion of the atom of the positive charged particle inside any electric field like this will be parabola. It will be parabola only. Okay. Am I audible? Yeah, there is some sort of lag, but yes, I am audible on this side. Okay. So look, I can write one more thing now. Look better. Look, I guess y is equals to 1 by 2 qe by mt square. I guess we had one equation like this. Look, so you can write, if let's suppose t is constant, up to some certain point t is constant. Look, 1 by t is constant, ma e is constant. Electric field is uniform. So can I write y is directly proportional to the q by m? Simply indicate the more deviation. Why? What is y? Y is more deviation. More deviation, more q by m ratio. More q by m ratio. I guess you have one numerical in your NCRT. Electric field and charges. The book back exercise. On the second page, you have two pages, the book back. Now on the second page, you have first numerical like this. And you have same graph, same kind of diagram like this. So look, you have to find more deviation. Look here now, more deviation, more q by m ratio. More deviation means more q by m ratio. That's all. Okay. One more point. Let us do 1 2 numerical, then we'll just complete our class, because my class is for our 90 minutes only, right? Look now, 1 2 numericals we will discuss here. One numerical that we have from IIT. Numerical like a charged circular ring. On the charge we have plus q charge, and the radius of my circular ring is r. Okay. Then a point charge q, a point charge minus q is placed. A charged particle minus q is placed at the center of a ring. Now this charge, it is displaced, but slightly. It is slightly displaced along x-axis. Along x-axis. First case. Then what happens? Is it SHM motion or is it oscillatory? Second one, for any general value of x, same SHM or oscillatory. Look beta. We have a charged circular ring like this. Its radius is r. This is my axis. Okay, so we have a minus q charged particle at the center. Here we have here minus q charge. Done. Here we have a minus q charge. Now we displace minus q charge along x-axis here. Up to this particular point, we displace it, but slightly displacement, slightly. That means it is x, and x is very less than r. So if charged particle is here, then I release it. So what will happen now? This q charge on it, it will exert a net electric field like this and force like this. So it will go like this and come back like this. If the distance is very small, so we can call it as a SHM. We can call it as a SHM. But let's second point. If we are having the here, if it is, let's suppose x dash. If my x dash is equals to or more than my radius, so it will be then oscillatory. Simple. When there will be SHM, if the distance of displacement of particle is very small as compared to the radius, it will be SHM. And if the displacement of the particle from the origin is more than the radius of the ring, it will be the oscillatory motion, not SHM. Done? Easy? Okay. Now I guess we have a lot more things to discuss now. It will take some time. So what I can do now? One second. What we will can do now? So in next class, we will continue from their point now. Okay. So in next class, what we will be doing? Graphical things, graphs. Next class. Then we will be dealing with forces, then flux. These three things we will be discussing next class. If time permits, we will be discussing Gauss law also, right? Gauss law also. And I just told you, in back class also, our class will be of 90 minutes, not more than 90 minutes. Okay. In next class, we will be starting from graphs. Done? If you have any confusion or anything like that, you can just reach out to me by Telegram. You can go to my Telegram channel. There you will find my Telegram username of my personal. You can just ping me a message there also. I guess for today it is more than enough, no? We had a very good discussion on the properties. Then let's continue from tomorrow. Tomorrow is Eid, na? So tomorrow will be off. Tomorrow is Eid, so tomorrow will be off. Okay. I will inform you in the group, no? I will just inform you in the group. There is no issue. One more thing we have to keep in mind that we need to end the syllabus before September. So that is the end date. So let us hope for the best for all of us. So bye, beta. Bye. Thank you. Bye.